Welcome to the second lecture of modern digital communication techniques. So in the previous lecture we got an review or introduction to digital communications while viewing it with an experience of analog communications. So what we did was harping on the fact that you have already done a course on analog communications. We tried to explain to you how would you look at a digital communication systems with that knowledge, and what changes would it require. So effectively, if we would summarize, we are going to use almost the entire knowledge of analog communications to establish a digital communication system. However, the input message that we do, that means in the previous lecture what we said is, suppose the input source is an analog source, that means if we have this analog waveform, what we said is you would have to first convert it into discrete, that means let us say you quantize it into these levels, and once you quantize these into these levels, so your waveform might look like this, and so on, and this one you pass on to a carrier. And then we said that, well, this is the first step towards the transition, and now we again said that let there be a digital source. So if you have a digital source, end of the day this information is saved in forms of ones and zeros in your computer in a file, or if it's a smartphone or a mobile or a memory device, it's again stored in form of bits and bytes. So those are also ones and zeros. So now if you have ones and zeros and so on, you could translate these to two different levels, a level for level 1 and a level 2. So whenever you encounter a 0, you would send level 1 for a certain duration of time, whenever you get 1 you would send level 2, and so on and so forth. So this indicates there is a 0, there is a 1, there is a 0, there is another 1, there is another 1. So this is matching with respect to this particular signal, right? And at the receiver, what you are supposed to do is we would have to choose a threshold. So if the received signal is below the threshold, I would decode this voltage to indicate a 0, and this level of the signal, let us say electrical signal, to indicate a 1, and I would again regenerate my signal. This is what we said. So at this point I could use this signal to modulate a carrier, and the entire study of analog communications would come into play. That means the message waveform is this. This is the particular message waveform, and today we will take off from this particular point and we continue there. But just like to mention at this point that when you are looking at analog communications and you have digital communications on the other hand, typically if we close our eyes and think of an analog communication system, what comes to our mind is generally pictures of oscillators. We think of amplifiers, we think of filters, etc. Whereas when we think of digital communication system, so when you think of analog, the picture that you get in mind is this. If you think of digital, the picture that we get begins with the picture of bits. If it's a little bit more advanced, then we would think going beyond bits, we'd go to discrete. So when we say discrete, we mean discrete in amplitude and in time. So when we have these two things, this amplitude, this is actually a discrete signal that we're talking about, and if it's only two levels, it's basically binary. So in other words, we are talking about samples, right? And the other thing that comes to our mind is digital signal processing. So, as we said last time, this harnesses the power of digital signal processor. So, this kind of summarizes in some sense that when we talk of analog or when we talk of digital, what are the different pictures that come into our mind. Today we will spend some more time in trying to explain that when you take a digital communication system, what are the ways one should start looking at a digital communication systems. We'll spend a few more time on this before we actually begin with the details and nitty-gritties of a digital communication system. So, let's continue with this, and we can define in general terms a digital communication system we can generally talk about, these are our systems. We can talk about generally, we can say generally digital communication systems are designed with the target, we can write this, of transporting, we are using a bit layman term in the beginning, transporting bits. Okay. So, earlier it was messages. So, from messages we have now come to bits, and if you are a little bit more advanced, you can say that it is involved with symbols. So, it is transferring of symbols from the transmitter. We are all familiar with the transmitter, and we will use the notation Tx in our discussion, to the receiver, which will denote by an Rx. Okay. With now there are certain conditions, with minimum probability of error, where further we have also stated where each symbol occupies a finite duration while being transmitted. Now, when we put forward this particular statement, we are actually bringing in a few important words for the first time in this particular course. So, we will spend a little while trying to elaborate on them so that we get into the mode of thinking in those terms. So, one of the things that we have made quite different compared to the analog communication system is this symbols or bits, one of the things here. And the second thing that we have here are the probability. This is the second term that we have. Okay. So, this is the second term that we have, and well, if you can think of errors, it's okay, it's another third term that we can talk about. And we have also said that the symbols occupies a finite duration while being transmitted. So, in that sense, this can also be thought of as the fourth thing, but these are too much details. At a very top level, we can talk about these two. So, essentially we are saying that we are not transferring anything other than bits or symbols. So, that is fundamentally different. We are beginning with bits, we are ending with bits, or beginning with symbols and ending with symbols. That is one arena. The second thing we are talking about is we have brought in a criteria of probability. This is also important to note, and these things are pretty different from your earlier notion of a communication system. Now, this is not very obvious why we are talking about probability. About bits and symbols, it's somewhat clear to you going by this particular picture, but we'll see more of it why we talk of bits and symbols. Okay. So, with probability, I'll talk about it anyway in this probably in this session or maybe in the future sessions, that why do we bring in the notion of probability, because the way we look at communications in digital systems is quite different than earlier versions. So as we move ahead, so for digital communication systems, it is important that we look at sources which are discrete in time and in value or in magnitude. So this is one of the requirements of digital communication systems, and we have already mentioned that digital communication systems are like that, but now we are putting it in a different way. We are saying that for a digital communication system, you require the source to give discrete levels of output and in discrete instants of time. So now we are defining that, and so this actually means that if you have an analog source, if there is an analog source, this must be converted. So you have to convert the output using an analog to digital converter. Okay. So you have to send it through an analog to digital converter. This output has to go through a quantizer, and the quantizer output can further go into an encoder, and once it has passed the encoder is going to generate bits, or it can also generate symbols, right. So this is how the things will be. So these symbols that you have would finally go into something called the channel encoder. Because these are still symbols which are in abstract form, so one has to convert this again. You convert it to a form which is more suitable to the channel. We will see this in a short while. In this particular course, as we go down in time, we will take up the source encoding in a few lectures, and in that we will talk about the analog to digital converter, we will talk about the quantizer, we will talk about the encoder, and we will spend a lot of time in this encoder, and while doing so we will be clear that why we have talked about probability, one particular area that where probability plays a vital role. Now once we have these symbols, when we say it gets converted to channel through the channel encoder, what we mean is that the channel is basically the physical channel that we are talking about, and we'll soon show you, or we'll soon tell you, that when you have to send this abstract symbols into the channel, you must convert it. So that's what we are going to do now. So typically the symbols they get converted to waveforms. And why waveforms, and what kind of waveforms if you think of? So these are like you can say they are modulated, in other words. So what you have is these symbols, they actually are used for amplitude modulation, they could be used for frequency modulation, they could be used for phase modulation, and they could also be used for intensity modulation if you are doing light based communication. So if we look at our first lecture, and when we say this, so these symbols, these could be representing symbols, the encoding over here, this amplitude level, they could reflect the symbols. So this could be symbol 0 0 0, this could be 0 0 1, or this could be 0 1 0, and this could be 1 0 0 this particular level, and this could be 1 0 1, and so on and so forth. These are different symbols, and those are used to modulate this particular carrier. So that is what we meant in this particular statement. So they are converted to the waveforms by means of modulation, and this is what you studied in ANACOM, analog communication. Okay. So as we are going into digital communications, we will not go into this part, rather we will almost always remain till the point you are converting them to waveforms. So things will be clearer slowly with time as we go on describing each of the modules in more details. So when we talk about the channels, so channels could be different types. There could be different types of channels. One of the classification could be a wireless channel. The other type of classification, you could say it's an optical fiber. The other one could be a twisted pair. Then there could be coaxial cables. So now if we look at these different channels, one can say that if it's a wireless channel, then you have to modulate the electromagnetic wave. If it's the optical fiber, of course it's the light, so you are still talking about EM waves, but the kind of modulation could be different. You can talk about controlling the intensity of light that goes into the fiber. So if there is a 0, there is some amount of intensity. If there is 1, there is a higher amount of intensity possibly. One could go for on off keying, on for the period of 1 and off for the period of zeros, or vice versa, that could happen. If it's twisted pair, you can talk of two different voltage levels. If it's coaxial cables, again you can send different signals onto it. So basically the same symbol before going into the channel could be all same, that means we are talking about symbols, but when it is sent over different types of channels, you could send it differently. For example, we can say that you are interested in sending the image, which is again a sequence of zeros and ones, to a friend or to the other side of the network, to a node or to a computer, to a phone, to a Wi-Fi device. It goes to a wireless media. So then this zeros and ones could be used to modulate the amplitude or the frequency or the phase of the electromagnetic wave. If it's the wireless, if it's connected through the optical link, it could be visible light optical link, it could be laser, it could be wireless optical, it could be fiber optic. Then the same zero could be used to change a different property of the different you can say physical resource. Here it is the spectrum of electromagnetic waves which comes under the light, visible light band, or the infrared, or even the ultraviolet. So basically you are choosing a different frequency. It's similar, but you're opting to a different property. When you go to twisted pair, instead of sending electromagnetic waves, you can directly send electrical signals, which is in form of voltage across these twisted pairs, and you can communicate a sequence of zeros and ones to the other side. If it's coaxial cables, again you modulate the waveform and you send it across through these waveguides. So these acts as waveguides. So what we are trying to say, that the same symbols could be used and sent across different channels. So our study would be limited to this region where we generate the same symbols, and this is almost independent of this part. When it gets converted to a particular type of channel, that means this is matched to a channel, that is waveform matching. What we will discuss is, of course, there is something called the pulse shaping, which is corresponding to the properties of this channel. But again we can characterize the channel in terms of its impulse response, in terms of its frequency response. So if we can characterize a channel in terms of its impulse response and frequency response, we can still design pulse shapes in baseband. Probably I'm using the term for the first time, in baseband, that means not with the carrier, that means without the carrier, and still design the system. So the rest of it would be the digital to analog conversion. Well, we can still remain in that part, but from analog signal, electrical signal, to the appropriate is not what we are going to cover in this particular course. So that should be noted. And again what we can see is these type of channels are continuous in nature, and when we talk about this is discrete. Right. So, I hope some things have improved from the last discussion about analog and digital communication systems, where the boundary comes in. It is very difficult to define an exact boundary, but it is we are very close to it in defining a separation between analog and digital communications. So that's the right perspective that we need to set before we actually set forth into the journey of digital communications. Okay. The next very interesting thing in the study of communication systems, especially digital communication systems, is noise. I would say it's a very interesting entity. I don't know if I am hurting somebody, but it's really a very interesting entity. So generally we hate noise, right? We don't like to hear noise, we don't like to experience noise, but again, very silly thing to say, but without noise your life as communication engineer would be very limited, because noise is what has given rise to all kinds of innovation and all kinds of smart and advanced communication system design. So as communication engineers, you can say that you live on noise. Had noise not been there, things would have been very different. So when we think of noise, generally reminds us of randomness. It reminds us of chaos. So I could write down the word randomness or chaos. So when we talk of randomness, what comes to our mind is distributions, probabilistics, chances, right? What's the chance that I send a 1, it becomes a 0. I send a 0, it remains a 0, or I send a sequence of zeros and ones, it gets converted to another sequence. This is highly possible because of noise. For example, if we try to look at the picture that we have drawn earlier here. So here, if we add noise to this when it's being sent over a piece of wire, the signal could get distorted. So for example, we use a similar picture. I have sent, let's say, this. Because of noise, this when noise gets added, what I receive could look like this, right? And now at the receiver, if I am making a decision threshold here, what I am going to receive is probably a 0, and then in between I might get a 1. I get a 1, in between I get a 0 because of here, I get a 1, I get a 0, I might get 2 1s, I might get 0 1, and 1 I 1 a 0 a 1 a 0 a 1 1, and so on and so forth, because the signal has crossed this threshold at some point. So that means the signal, the input sequence gets completely changed when it comes to the receiver. So noise is very important, and since this happens, we are left with no choice but to process the signal in such a way that we recover the most and we make minimum errors, and that's how we started off defining the communication system when we said that target of transporting bits or symbols from transmitter to receiver with minimum probability of error. So why we say this? Because when this happens, we don't know next time when I'm going to send a 0 1 0 0 whether the same pattern of noise is going to come. It's absolutely unknown, nobody knows, right? So we have to be prepared to handle this kind of uncertainty in the system, and that's why we study digital communications, so that we can design an appropriate transmitter, we can design an appropriate receiver, so that we can minimize these kind of errors, right? So we would rather say that one should learn to live in the presence of noise. It's not possible to eradicate it completely. Some things will remain, but we can definitely reduce the effect of noise on the received signal. That we can definitely do, and that is what we will do in our course as we progress with time. So, our objective, you can say, is to achieve the most in presence of noise. I am not writing that down, that is pretty obvious. So, although noise is random, I mean, since you have studied noise probably in analog communication as well, but still there is some kind of irregularity in this. That means there is some kind of a statistical regularity. Statistical regularity would mean that although I know that there is randomness, that means I cannot predict what's going to happen in the next moment. That means when I send a 1, whether that 1 is going to become a 0 or it's going to remain a 1, I don't know. That's randomness. But I can tell for sure, if I send 1 billion ones, what fraction of those would get converted to a 0 and what fraction would remain as it is. Now, this fraction is sometimes called the probability of error, the 1 getting converted to a 0, and 1 minus that fraction is basically the probability of it remaining correct. So, this fraction or this probability is going to be consistent, and it's going to be consistent with larger observation windows, and that brings us to the notion of stationarity. So, of course, we will be using the notion of stationarity, because if it is a non-stationary system, that would mean that when I set 1 million bits now, and let us say I send 1 million bits a few while later, the percentage which becomes 0 in the earlier case to the percentage which becomes 0 in the later case across the same system, if that varies significantly, then we are handling a non-stationary system. If we are handling a non-stationary system, then it's very difficult to design a communication system for them. So, at least you can think that we will be handling a piecewise stationary, if not anything, at least for the time that we are considering the system, its statistical properties does not change with time. So, of course, there are different definitions of stationarity. There could be strict sense stationary, wide sense stationarity. We will be mostly sticking to wide sense stationarity. So, at least that again gives us a hint that why we need to use this definition of probability, or why we said that probability is a very important term in the study of digital communications. Right. So, further you will note at some point that this noise is actually represented in almost infinite dimensions, means wherever I take a component, I get a component of it. So, in other words, it's very difficult to define noise completely, and if you use a statistical means of define it, well, you can define it in some way. So, that means in the statistical sense there is regularity, so I can handle it in a statistical fashion, and I will design my transmitter and receivers in a statistical way accordingly, right. So, that is what we will be doing. The receiver, of course, well, we can write in brief over here. The receiver is the inverse processing of the transmitter, right. That's the next part, and in our communication systems we will actually do a lot of receiver design, a lot of components of receiver, and I have told you in the introductory lecture, if you have gone through it, that in a digital communication system, the receiver plays a very important role, where there has to be a synchronization entity, that means which synchronizes the carrier, which you may have studied in analog communications as well, carrier recovery, and followed by you have timing synchronization, because as you are seeing that here, time is a major factor, right. So, we know that 1 was sent in this period of time, right. If 1 was sent in this period of time, in that case at the receiver, even if the receiver generates a 1 0 in this period, we should actually take one of these two, or we should take a representative single bit for that duration of time. So, this indicates that time synchronization plays a major role in digital communications. So, the kind of time synchronization we have tried to depict over here is a bit synchronization or clock synchronization. There is frame synchronization. Beyond that, as we talk about these channels earlier, as we talked about these channels, each channel is unique in its own way. So when we send the same bits 0 1 0 1 0 0 across a wireless channel or the same sequence over the optical fiber channel, the chances that sequence 0 1 0 1 0 0 is going to remain the same in these two different channels is very different. They have to be very, very different. Now that depends upon the channel properties, which includes the amount of noise in the system. Usually we ascribe noise to the amount of noise at the receiver. So basically when we talk about channels, it's the amount of distortion that these channels bring in. So there needs to be equalization of the effects of the channel. So first the channel needs to be estimated, followed by equalization of the channel. Now you can easily see that these few things as I have described is not required in this part, which is the transmitter, before it sends into the channel, right. So receiver has to do quite a few extra things which are very specific to the system, but again we'll find methods to represent the different channels as we have here in an abstract form, so that we can capture the effect of these channels on the signal that we are getting, that we are transmitting. That means we transmit a signal, let's say x of t, we receive a signal which is y of t. So y of t is a function of x of t and the channel properties. So if we can abstract and make a model of the channel, which we'll of course show you in this course, we can reverse engineer, we can recover the effect of the channel and reconstruct the signal in its original form, so that we get as less error as possible. So those are some of the things we'll slowly get to know with time in this particular course. Thank you.